All right, guys, we're going to go over section 13.5, which is called the simple pendulum. Simple pendulum is just basically any mass on a string. We've used simple pendulums in the past for some other reasons, especially like energy transfer. But in this section, we're going to specifically discuss simple pendulums in simple harmonic motion. And I guess there's something a little bit of weird with this, is that all the SHM formulas we have, dealing with like time period, frequency, all those little ones in the SHM section, are only applicable at small amplitudes. So here's what that means. When we measure the displacement of a simple pendulum, like the simulated one, we actually measure the displacements through the angle to the fixed position right here. So you can see I have a pretty small angle. This dotted line represents the equilibrium position. So we got a pretty small angle from either to the left or the right, displacing from the fixed pivot position. And we're going to spend most of today discussing why those formulas for SHM only are good for small amplitudes. And it all goes back to something we learned about Hooke's law. So I'm going to flip to the notes I have posted for section 13.5. And we'll do that diagram in a second. But there's a statement back with Hooke's law when we were dealing with spring pendulums that said F equals Kx, or negative Kx, to be specific. And when we defined SHM originally, there was a statement based on Hooke's law that for something to be an SHM, simple harmonic motion, the force had to vary directly with the displacement. That meant the F, if we're talking spring and Hooke's law, the F had to vary directly with the X, basically. And it did, because F equals Kx. Now, we got a little bit of a problem with string pendulums and simple pendulums like this. Now, we're going to consider also, just a little note here, the string or whatever is suspending the mass in a simple pendulum. We're going to just consider it massless to simplify this model right now. And it doesn't stretch. All right, so now we'll get to the diagram. So again, this line represents the equilibrium position if it's at rest. Here's our angle, referred to as theta, that represents the displacement away from that equilibrium position. And let's draw the object, the mass, right here, and basically a free body diagram on it. We have the tension in the rope pointing up, its weight pointing directly down. But we can see that I have split the weight into two components. And we're going to call the component which restores the simple pendulum back to equilibrium, that basically points along the arc path right here, mg sine theta. And this one that really puts the tension in the string is mg cosine theta. You could kind of think what I did here was make like the arc the x-axis, because it swings through the arc, and at every moment put an x-axis there, and the axis the tension's on being the y-axis. Whatever way you think about it, the geometry of the situation comes out. If this is theta, this is theta. You could think of the mg vector, the weight vector, as a transversal, and that's just some basic geometry. So regardless of the case where you want to view axes, if that is theta there, that's how you do some basic trig to get mg sine theta here and mg cosine theta here. All right, so what this proves, our point right now, is mg sine theta is restoring force. The component of the weight that wants to bring us back to where we were. You can see it kind of points along that arc path. So therefore, this restoring force can be written F equals negative, just there for the same reason negative is in Hooke's law, to bring it back, mg sine theta. We got a problem with this right now, because with Hooke's law, F equals negative kx, the force is directly proportional with x. But the problem here is the force is not directly proportional with the displacement. Remember, the displacement line is the displacement angle theta. In this formula for this restoring force in the simple pendulum, F is directly proportional with the sine of theta. And that is not how simple harmonic motion is defined. However, you could prove on a calculator if you really wanted to, but for now, just take my word for it. At small amplitudes, the sine theta is approximately the same thing as theta in radians. So if I took some smaller angles, like 5 degrees, 10 degrees, probably up to about 15 degrees, different resources define what small amplitude means slightly different. I usually say small amplitude between 0 and 15 degrees for this displacement angle up here, okay? So if I took any of those angles from 0 to 15 degrees, turn them into radians, and took the sine of any angle between 0 and 15 degrees, that's not an equal sign right there. That's an approximate sign. So the sine of a lower angle, 0 to 15 degrees, converted to radians, and take the sine of is approximately equal to that angle in radians anyway. It's extremely close. So if that's the case for small angles, I could put, instead of sine theta in this formula we got from the body diagram, I could replace it with just theta, since they're so close to the same thing, right? So now I get a formula only for small angles where F is proportional with theta. And now we can use simple harmonic motion formulas and ideas on simple pendulums. But as theta would grow, especially higher than 15 degrees, the sine angle in radians and the angle itself in radians start to stay further and further away, and you can't make this approximation. So simple harmonic motion ideas and formulas will work past that. Let's define a few other things here, because you can see in this right here, I'll replace theta with x over L. And that's because of another geometric thing that I'll go up to the diagram here in a second and show. X equals L theta is the arc distance. So if I go up to my formula, see how I draw X as like the arc distance here, because that's the path of which the mass would take while swinging here. Just from a little geometry with arc length and whatnot, X equals L theta, all right? That arc length. So I could use that formula, solve it for theta. Theta would equal X over L, and I erased it there. So now I have the same formula written a different way, while putting in and substituting in that formula. And I just came down here and made it look more like Hooke's law so we understand it more. Remember, Hooke's law for oscillating SHM springs in the force restoring force was, one more time, F equals negative kx, where k was defined as the spring constant. Remember, the spring constant is made up of features of the spring, such as material it's made of, amount of coils, things like that, size of the coils that makes the spring tighter or looser to bounce the object back and forth or up and down. Well, now we have a formula that looks kind of like that, but instead of a K, we have the restoring force equals negative mg over L times x, the distance along the arc. So what that really means, why we wrote it like this, is because this is known, this whole mg over L is known as the force constant K of a simple pendulum, meaning that the features of a pendulum through its force and arc distance and how maybe like quickly it will get back and forth while swinging depends on the mass that's hanging there, the gravitational field we're in, G, and the length of the string. So all that together makes the force constant of a simple pendulum. So with all that in mind there, and going back to some formulas, general formulas in the original SHM section, which I believe was 13.3, we could rewrite some of the formulas. Some of them will look exactly the same, but we could rewrite some of them more specific for a simple pendulum. So as we define this, the simple pendulum constant is mg over L, and this is an old formula. The angular frequency equals square root of the constant over m. Well, if the constant is now mg over L, I'm going to replace that here and clean it up. We can see an m and an m cancels. So the omega for a simple pendulum is square root of g over L. This is only true for a simple pendulum, a mass on a string, it's not spring, excuse me, a string swinging back and forth at small amplitudes only. All right, again, small amplitudes, we're going to say about between 0 and 15 degrees. I'm going to make some of these other placements then. Since omega is that, here is another SHM formula. F equals omega over 2 pi. Frequency equals angular frequency over 2 pi. I'm going to plug square root of g over L in for omega, and we can make it look like this. And finally, here's some with period. Remember, period was the inverse of frequency. And anywhere we see omega, we could plug that in up there as well. These are all specific formulas, one more time. And they're easy formulas to use, just it's important to know why and where they came from as explained above. So we're going to do a quick, hopefully very easy example, and then assign you guys some problems on this stuff in the next video.